Hello and welcome to this presentation on solution of differential equations using Laplace transforms. This presentation assumes you're familiar with the use of Laplace transforms and inverse Laplace transforms, and that you have an understanding of partial fractions and also of completing the square. This presentation will outline the solution of first and second order differential equations using Laplace. The introduction will outline the solution process, which is 4 generic steps. The inverse Laplace transform table will be repeated here for convenience, so we will be using that. Example 1 will be a first order differential equation that will use linear partial fractions to aid solution of the standard forms for the inverse Laplace transform table. Example 2 is a second order differential equation. Within that we will again use linear partial fractions. Example 3 is a second order differential equation which will use completing the square within the solution, and example 4 is a second order differential equation within which we'll have repeated linear factors to consider. We'll end with some tutorial questions. Okay, we're going to outline the procedure here for solving differential equations using Laplace transforms. 4-step process here, 4 generic steps. So step 1, we're going to take Laplace transforms of both sides of the differential equation, whether it's a first or second order differential equation, by applying the formula for Laplace transforms of derivatives. These equations are labelled 3 below and 4 over the page, and we've derived them in a previous handout. So equation 3 here is for a first order differential equation. So the equation states Laplace of the first differential of t is equal to s times the Laplace of the function of t, take away the value of the function of t when time t is equal to 0. I've called that equation 3a here. I've also put 3b below it, just using different notation. The function dash notation is being replaced by dy by dx notation, and the f function of t's have been replaced by y. So it's a different notation, the equation is exactly the same. Equation 4 here looks at the second order differential equation. The Laplace transform of the second derivative of the function of t, we're told is written as s squared times the Laplace of the function of t, take away s times the value of the function of t at time t is equal to 0, take away the value of the first differential of t at time t is equal to 0. I've called that equation 4a, and again underneath it I just put the same equation but using slightly different notation that is sometimes used in the questions. Step 2, we are going to impose the initial conditions. These will be stated in each of the questions. The value of the function of t when time t is equal to 0, and the value of the first differential of t when time t is equal to 0. So these will be put into the differential equation for step 2. Step 3, we're going to algebraically rearrange the equation. Don't forget the whole essence of Laplace is taking a differential equation which is quite difficult to solve in time domain, in the real world if you want to think of it that way, and we're moving into the S domain, the Laplace domain, where the differential equation now becomes an algebraic equation. So we're going to rearrange in step 3 the equation for the Laplace of y. We're going to make that the subject of the equation. Step 4 then, we're going to determine the function of y. We're going to solve our differential equations. Now this may involve the use of partial fractions. It may involve the use of completing the square. If our functions are not in standard form, we use partial fractions or completing the square to try and make them into standard form, from where we can take the inverse Laplace transforms of each term by looking at our table. Okay, we're just going to recap the linearity property of Laplace transform, something we've mentioned in a previous presentation. If we have Laplace of A is a constant, times the function of t, plus b, another constant, times another function of t, what linearity allows us to do is to take the constants outside of the Laplace transform. So the A can come outside of the Laplace transform, and then plus the b comes outside of the Laplace transform. Sometimes that helps us simplify our solutions and enable us to recognise the formats of inverse Laplace transforms. Just for recap here, in table 1 here I've got the inverse Laplace transform stated. Some of these we've seen before, so I won't labour this with you. And here's the second part of the inverse Laplace transform table. We'll be referring to this in the problems we're going to look at in a moment. Okay, so looking at example 1 here, it's a first order differential equation we're asked to solve here. It's dy by dt, take away 2y is equal to 3. We're given that at time t is equal to 0, the y is 4. Okay, so that's like our boundary conditions here. So we're going to follow our generic step through. So step 1, we will take Laplace transforms of both sides of the equation. So the Laplace of the dy by dt, take away 2 times the Laplace of y is equal to the Laplace of 3 on the right hand side. From our equation 3 here, the first order differential equation, we can now write the dy by dx term as the Laplace of the function of y, take away the value of the function of t at time t is equal to 0, then take away the 2 times the Laplace of y. On the right hand side, you need to recall your Laplace transform tables. A constant, if we go from the time domain, a constant into the Laplace domain is written as the constant upon s. So that's where I get the 3 upon s from the Laplace transform tables. Step 2, I'm going to impose the initial stated conditions here. We know that when t is equal to 0, the y is equal to 4. So I put that into my equation here for the y, bracket 0, close bracket from above, becomes minus 4. What I'm doing next is I'm factorising here on the y, for Laplace of y term here. As you can see, it's a common factor here. So and here, so I will get s minus 2 in bracket and the Laplace of y outside. So I'm factorising on the Laplace of y here, and I keep my minus 4 separate. On the right hand side I've still got my 3 upon s. Okay, step 3 here, we're now going to rearrange the equation to make the Laplace of y the subject of this equation. From the previous slide, I would add 4 to both sides to get the 4 on the right hand side, and I would divide throughout by the s minus 2 in brackets to get that on the denominator. So now I have 3 divided by s plus 4, all divided by s minus 2. On this next line, what I'm going to do is take the s to the bottom line, because 3 is divided by s and is also divided by the s minus 2. But if you notice, I've added an s against the 4 because the 4 is only divided by the s minus 2 in the brackets. It's not divided by the additional s that the 3 is. So by adding the s to the 4 on the top, that cancels with the s on the bottom. So I still got, if you like, 4 divided by s minus 2. Just take a moment to think that little step through for yourselves, that you understand what's going on there. Step 4, we're going to start to take the inverse Laplace transforms now of our functions. What we notice about the denominator above is that the s open bracket s minus 2 close bracket is not a standard form. So we do not have a standard form in our table of inverse Laplace transforms. So what we're going to try and use here is something called partial fractions, which we've covered before, and there are 2 checks we need to be aware of before we can commence the partial fractions. The first is that the numerator of the fraction, the top line, must be lower ordered in denominator, and that's true here because the numerator has an order of s, and the denominator, if you expand the bracket, would have an order of s squared. So that that check is true. And also, does the denominator factorise? Well, it's already factorised in terms of the s open bracket s minus 2 close bracket. This is what's called a linear factor. We have two linear factors here, the s and then the s minus 2 in brackets, and from our previous work we write that in its partial fraction form as a over the s plus the b over the s minus 2. So equation 1 is the equation we need to now solve for the constants a and b. Okay, I just repeated the top line here for convenience from the previous slide. What we have to do now is solve for the constants a and b in our linear partial fractions here, and to do that I'm going to use the cover-up rule. The way the cover-up rule works is we have to consider what value of s do we need to make that denominator go to 0 in the first term. Well, obviously that s value has to be 0, and the way the cover-up rule works is we now cover up this s on the left hand side and we put the value of 0 wherever we see an s in that part of the fraction. So if you take the top line, we've got 3 plus 4 times s, so that's 3 plus 4 times 0 in this case, over, looking at the bottom line, the s minus 2, that'll be 0 take away 2. If we do the arithmetic on that, we will find we get a negative 1.5 for the value of constant a. Similar process now to find the constant of b using the cover-up rule. What value of s do I need to make this for the denominator to tend to 0? Well, s is equal to 2 in this case. 2 take away 2 will give me 0. So this time we cover up the next term on the left hand side, which is in the denominator, which is s minus 2. So we cover up the s minus 2 this time, and we're going to put the value of 2 wherever we see an s on that left hand side. So again, top line 3 plus 4 times s, but 4 times 2 this time, all divided by on the bottom line which got the s, which is 2. Again, looking at the numbers on that, we end up with a value of 5.5 for constant b. Okay, from the previous slide we found the value of a is minus 1.5, so we've got a partial fraction of minus 1.5 upon s, and the value of b was 5.5, so we've got the partial fraction of 5.5 upon s minus 2. We now refer to our inverse Laplace transform tables, and we try and look for standard forms here. Looking at the first partial fraction, I think that's a form 1 upon s. Don't forget the minus 1.5 is basically a factor, so we have a sort of minus 1.5 times 1 upon s, if you want to think of it like that. So I think we've got a solution for the first partial fraction, and the second partial fraction again fits the format of 1 upon s minus a, with the 5.5 being a factor. So our solution for y in this case will be the minus 1.5, which is the factor, times by the 1, which is the inverse Laplace transform of 1 upon s, and then plus in this case the 5.5, the factor, times by the inverse Laplace transform of 1 upon s minus a, noting that a is equal to 2 in this case, so the solution is e to the at, which becomes e to the 2t. All I've done in the final line is just rearranged to put the positive number in front of the negative number. Okay, example 2 here is actually a second order differential equation. It's 2 times y double dash, and y double dash is d2y by dx squared, plus 5 times y dash, which is 5 times dy by dx, take away 3 times the y is equal to 0. We've got some boundary conditions again. When x equals to 0, and just note we're using x instead of t here, y is equal to 4, and the dy by dx, the first differential of y, is equal to 9. We need the extra condition this time because of the second order equation. We're going to follow our generic step through. So step 1, we're going to take Laplace transforms of both sides of the equation, and again using linearity I'm taking 2 outside of Laplace of the second order function, plus 5 times the Laplace of the first order function, take away 3 times the Laplace of the y function, and that's equal to, in this case, Laplace of 0 on the right hand side. Using equations 3 and 4 from our previous work, I will now put the second order derivative in to the expression, so 2 outside. This is the second order derivative here. In Laplace terms it's s squared times the Laplace of y, take away s times the value of y when x is equal to 0, take away here the value of the first differential of y when x equals to 0, plus, now this is the first order part of the equation, that's 5 times s times the Laplace of y, take away the value of the function of y when x is equal to 0 in this case. Then take away my 3 times the Laplace of y equals to the Laplace of 0. So step 1 done there. Step 2, going to impose the initial conditions, so we know that when the value of x equals to 0, y is equal to 4, and when the value of x is equal to 0, the dy by dx term is equal to 9. So we're going to impose those. So just looking at my line here, I get 2 s squared the Laplace of y, take away 4s, take away the 9 here. So I've put my conditions in there, the 4 and the 9 have gone into the second order part of this equation, plus then 5 times the Laplace of y, and there's the 4 going into the equation, take away the 3 times the Laplace of y is equal to the Laplace of 0. Okay, here I'm just expanding the bracket, I get 2 times the Laplace 2 times s squared times the Laplace of y, take away, then it's 2 times the 4s gives me the 8s, and then 2 times the minus 9 is giving me minus 18. Okay, here I'm just expanded by the 5, so it's 5 times the s times the Laplace of y, take away 5 times the minus 4 is minus 20, minus the 3 Laplace of y is equal to the Laplace of 0, or 0 on the right hand side. Okay, continuing on here, I just repeated the above line for convenience. Step 3 now, what we've got to do is rearrange the equation for the Laplace of y. So this is purely algebraic rearrangement here, okay? So I'll just take you through this briefly. Basically what I'm going to do is factorize on the Laplace of y. There's a Laplace of y there, there's a Laplace of y there, and there's a Laplace of y there. That's like my common factor. So I can write the Laplace of y outside of 2s squared plus 5s minus 3 in the bracket. I add the 8s squared to both sides to get on the right hand side, and I add the 38 to both sides to get that on the right hand side. The 38 comes from the minus 8 minus a 20. Okay, final step here, to find the Laplace of y, make it the subject of the equation, I just divide both sides by the bracket, so dividing throughout by 2s squared plus 5s minus 3. Step 4, this is where we need to take inverse Laplace transforms of our function to get to our original expression. But again, you will notice from the above expression, it's not a standard form. We cannot look that one up in a table. In this case, we're going to use partial fractions again. They are both linear partial fractions in this case. I'm going to use the same process as I did in example 1 here. So on the left hand side down here, I have my function. Notice what I've done is factorized it in the bottom. Don't forget there are 2 checks we always have to do here. Is the numerator lower order than the denominator? Yes, it is. I've got an s on the numerator and I've got an s squared in the denominator. And does the denominator factorize? And yes, it does. It factorizes 2s minus 1 in brackets, s plus 3 in brackets. Okay, so looking at my partial fractions here, I will have a over the s squared 2s minus 1 plus my b over the s plus 3 term. Okay, so I need to now solve for constants a and b. Okay, just repeating the top line for convenience here. So now what we've got to do is find the values of a and b, our constants here, for our partial fractions. We're going to use the cover-up rule again because that's nice, quick and easy here. Don't forget the way the cover-up rule works. We have to find the value of s that will make the denominator go to 0. So I think it's clear to see that s is equal to 0.5 in this case. 2 times 0.5 gives me the 1. Take away the 1 goes to 0. And what we do then is put the value of s into the equation, but we cover up the 2s minus 1 bracket. So I'm putting the value of s wherever I see an s in that expression. So following that through, 8 times s, 8 times 0.5, plus my 38, divided by s plus 3, so that's 0.5 plus the 3. We do the numerical work on that, we find that a is equal to 12. Similar thing for part B, for a constant b. What value of s do I need here to make that bracket go to 0? I need s to be negative 3. Negative 3 plus my 3 is 0. So again, following the approach through for the cover-up rule, I will now cover up this bracket here and put the value of s into the rest of the left-hand side of the equation. So following that through, that will be 8 times s, 8 times minus 3 now, plus my 38, divided by 2 times s, 2 times minus 3, minus my 1. If you follow the arithmetic through, b is equal to negative 2. So we solve for our two constants a and b. Okay, now we've got the value of a from the previous slide of 12 and the value of b of minus 2 in this case. We now need to find the inverse Laplace transforms of the 12 upon 2s minus 1 function and the minus 2 upon the s plus 3 function. We need to look at our inverse Laplace transform tables, and looking at the above partial fractions, they seem to fit reasonably well with the 1 upon s minus a. So I'm going to use that. I'm going to try that inverse Laplace transform and see how it works here. So just try and follow this through. I'll take the first term only. I'm going to find the inverse Laplace transform of the 12 divided by the 2s minus 1. Now that's not really in the form I want at the moment, because I want 1 over. So using linearity, I can take the 12 outside, so I can have Laplace transform of 1 over the 2s minus 1. But that's still not quite in the form that I want. I want s minus a on the bottom, and I have a kind of a 2s minus a on the bottom at the moment. So a little trick we're going to use here is I'm going to divide top and bottom and by the value of 2. So dividing 1 by 2, I get 0.5. Dividing by the 2s by 2, I get s. And dividing the minus 1 by 2, I get minus 0.5. So now I am in the form of the s minus a on the bottom, but I've got 0.5 on the top. But of course, again, using linearity, I can take the point outside the inverse Laplace transform function, so 12 times 0.5 gives me 6, and now inside the inverse Laplace transform function, I've got my 1 upon s minus a. So I suggest just look at that again, how we did that, rearrange that into the standard form there. But now I have my 1 upon s minus a, so looking at the inverse Laplace transform function, that goes to e to the a t in this case. My a will be 0.5, so I'll get 6 as the factor e to the 0.5, and this times x, because x is the variable I'm using. If I go to the second function, the inverse Laplace transform of the, in this case, 2 divided by the s plus 3, if I take the 2 outside the inverse Laplace transform function, I'm basically in the form of the standard Laplace transform function. Just notice it's a negative in the table and I've got a positive, so that would mean that my a value in this case will actually be minus 3 when I come to use my inverse Laplace transform function. So if you follow it through here, I've got exactly the right format here, as long as I make my a negative 3, then I've got my s minus a on the bottom. So looking at the solution there, it will be negative 2 e to the at or ax, a in this case is minus 3. All I've done on the final line here is just simply factorized on 2. Okay, go and look at example 3 here, kind of very similar format to the previous question. The only thing that's different here, you'll find in the solution of the inverse Laplace transforms will be using completing the square and not partial fractions. So again, I'm given my second order part of the differential equation, my first order part, and my function of y here is equal to 0. I've got my 3 conditions as for example 2. When x is equal to 0, I know that the y value is equal to 3 and the dy by dx is equal to 4. So following the process through, step 1, I'm going to take the Laplace transforms of both sides. So again, the Laplace transform of the second order part of the equation, plus in this case 3 times the Laplace transform of the first order part of the equation, plus 7 times the Laplace transform of y is equal to 0. From equations 3 and 4 we defined previously, I will now get s squared times the Laplace of y, take away s, times the value of y when x is equal to 0, take away the value of the first differential of y when x is equal to 0, plus 3 times s times the Laplace of the y function, and then it will be in a moment 3 times the minus the y naught function, which is the value of y when x equal to 0, plus 7 times the Laplace of y equals the Laplace of 0 on the right hand side, which is 0. Step 2 says to impose the initial conditions, so we're going to impose them now, and we're given the values of 3 and 4 to put into the equation in the appropriate places here. So I will now get s squared times the Laplace of y, take away 3 times the s, then minus the 4, so I'm putting the 3 and the 4 into the second order part of the equation, and then plus 3 times the s times the Laplace of y, take away again the boundary condition going in there for the minus 3 there, and then plus the 7 times the Laplace of y equals to 0. So just imposing my y naughts and my y dash naughts in the appropriate places in that equation. Okay, what I'm doing now is expanding the terms here, so I get s squared Laplace of y minus 3s minus 4, then plus 3 times the s times the Laplace of y, and then the 3 times the minus 3 gave me minus 9. So I've expanded that term there. The rest of the equation is the same. Okay, step 3. For example 3 here, we're going to rearrange the equation to try and make the Laplace of y the subject. So if I look at this first line here, I've got Laplace of y here against the s squared, I've got Laplace of y here against the 3s term, and I've got Laplace of y here against the 7. So Laplace of y here is a common factor, and I'm going to take it outside of a bracket. So inside the bracket I will get s squared from the first term, I will get the plus 3s from this second term here, and I will get plus 7 from this term over here. Okay, so that's factorising on Laplace y. I still have the minus 3y outside the bracket. I still have the minus 13 outside the bracket because they're not associated with Laplace of y. That still equals to 0. Finally, I just simply rearrange the equation. I add 3s to both sides, I add 13 to both sides, and I divide by the bracket, so I divide by the s squared plus 3s plus 7. Now I've got Laplace y as the subject of my equation. Okay, continuing on, step 4 now. What we're going to do now is try and determine y by taking inverse Laplace transforms. And I've repeated the fraction above here for convenience here. On the previous slide we have Laplace of y equals to the 3s plus 13 over the s squared plus 3s plus 7. Now what you'll notice if you look at the inverse Laplace transform table, that this is not a standard form. So we've got to sort of rethink this part of the question. So does the denominator factorise? And it doesn't in this case. You cannot factorise s squared plus 3s plus 7. So partial fractions can't be used in this particular case. So we've lost that approach. But however, we should be able to use completing the square here, and hopefully then make our denominator into a standard form that we can look up in our tables. The numerator does have the sort of appearance of s plus a in it, but at the moment the denominator does not fit the inverse Laplace tables. Okay, so we're going to try and use completing the square here to see if we can make these transforms into standard form. So using the usual process which we've highlighted in previous handouts, so I'm going to go through this fairly quickly here. First step is to write down the equation in the form of ax squared plus bx plus c. We're using obviously s as the variable here. So s squared plus 3s plus 7 equals to 0. The second step says we have to rearrange the equation to have all the s terms onto one side and the constant on the other, so I simply take 7 from both sides. The third step says we need to note the coefficient of the s term. In this case the coefficient is 3. We need to half that coefficient, so that's 1.5, and we need to square it. But when we square 1.5 we get a value of 2.25, and the fourth step says we need to add that value, 2.25, to both sides of the equation to keep the balance of the equation. On the right hand side I'm just simply bringing the numbers together. 2.25 take away the 7 is minus 4.75. Step 5, we factorise now on the left hand side, so that becomes s plus 1.5 all squared, the 1.5 being half of the 3, and that's equal to the minus 4.75. Step 6, we bring the constant back over to the left hand side by adding 4.75 to both sides. Now an additional thing I'm going to do here, looking at the inverse Laplace tables, I can see as a denominator of the form s plus a squared plus omega squared, and I kind of have that here. I have an s plus a squared here, and I have another value here, omega squared. If I was to square root the 4.75, which is 2.179, then I have an omega squared. So take a moment to think that through there. Again, it's a bit of experience of knowing what's in the inverse Laplace tables that has allowed me to think in the terms of the s plus a all squared plus omega squared as being a standard form. And in this case, our a would equal to 1.5 and our omega would equal to 2.179. I would encourage you to perhaps go back and look at that last step 6 as I've outlined it there, and make sure you understand it before you move on. Moving on here, now we've got Laplace of y is equal to, now it's 3s plus 13 over our completing the square solution, the s plus 1.5 all squared plus 2.179 squared. Again, still not standard form as such for what I need if you look in the tables, because I need an s plus a term on the top, and I don't have that at the moment. I have a 3s plus a constant here. So again, try and follow through this step here. What I'm doing here is I am taking 3 outside of the bracket here to leave myself with an s inside the bracket plus 1.5, and then this term here is going to be 8.5. Now I need to keep the s plus 1.5 in the bracket because I need the s plus a over the s plus a all squared type of term, so I need to keep that a 1.5 in the bracket. Because I've taken a 3 outside, I've basically got 4.5 when I expand the bracket. 3 times 1.5 is 4.5. So if I take 4.5 off of the 13, I will get 8.5. Okay, so again, just think that through. All I'm trying to do here is to make the numerator into a standard form of s plus a, and I'm trying to get a constant. The 3 is a factor that can be just taken outside of the Laplace inverse Laplace function. That's not a problem for us. Okay, the bottom line stays the same. What I can do now, though, is split it into 2 fractions here. I can have the 3s plus 1.5 over the solution we got from completing the square, and I can add to that the constant, in this case it's 8.5, over the s plus a all squared plus the omega squared we were using. Again, I need to think this through. The first term here is fine. I've got a factor that can go outside of the Laplace transform function, so that will leave me s plus a over s plus a all squared plus omega squared. That is a standard form in the inverse Laplace tables. But on the right hand side, I need to have an omega over an s plus a all squared plus an omega squared term. So I can't leave the 8.5 as it is. I need a 2.179 omega on the top to match with the 2.179 omega squared on the bottom. So again, just looking at my number work there, if I divide 8.5 by 2.179, I will get 3.9. So 3.9 times the 2.179 will give me roughly 8.5. So I've not affected the actual question. The question is still the same. But again, I've tried to make this in the form of an omega over an s plus a all squared plus omega squared. Again, I would encourage you to go back to that slide and have a look from the beginning of how we've rearranged the functions there. Okay, just repeating the Laplace of y function here with our two fractions. What we have now, basically, after using the completing the square method and rearranging our fractions algebraically, is a format that is in the inverse Laplace transforms table. In other words, our bottom line now is of the form s minus a all squared plus omega squared. If you look at these, we've got an s plus 1.5 all squared. I know the sign is different, but we can deal with that in a moment, plus the omega squared, the 2.179 squared. We actually have an s minus a all squared plus omega squared format on both of our fractions. So there are two solutions in the table that we can look at that fits the fractions we're looking at. If we look at the first fraction we've got with the 3 outside, the s plus 1.5, again, we've really got this format here of s minus a. Our a will be minus 1.5 in this case, and the 3 is just a common factor we can take outside the Laplace function. And with the right hand side, we've got 3.9 times 2.179. Again, that 2.179 is effectively our omega. We have an omega upon the omega squared term of 2.179 squared there. So again, we've got the format we need for the inverse Laplace transforms. So all we need to do now is actually apply those transforms. So taking the left-hand fraction above, the 3 open bracket s plus 1.5 close bracket function, if I write that now in its standard form of e to the a times cos omega t, noting that our a then is minus 1.5 and our omega is 2.179, we will get e to the at, that will be e to the minus 1.5 x in this case. Don't forget we're using x as our variable for this example, and it will be cos of the omega t, omega x in this case. The 3 stays at the front as a factor, factoring up the expression. Looking at our second fraction, the 3.9 times the 2.179 fraction, we will end up with e to the at again, e to the 1.5 minus 1.5x in our case, multiplied by the sine omega t, multiplied by the sine of 2.179x in our case. All I'm doing on the next line is factoring on the e to the minus 1.5x, and I'm also factoring on a factor of 3 in the next line. But those are just factorization exercises. On to example 4 now. We've got to solve this differential equation using the Laplace transforms. We've got a second order differential equation, 2y is a second order differential equation. That's d2y by dx squared in shorthand notation, plus a dy, that's the first differential of y, and that is equal to 8. We're given again 3 boundary conditions, this time when x is equal to 0, y is equal to 0, and the first differential is equal to 0. Now this example will take into account or require us to use both linear and repeated linear fractions, partial fractions. So we'll have to slightly change our solution sequence when we get to that stage. Rewriting the equation, I'll just put it into a more conventional format for us. So 2 times d2y by dx squared plus dy by dx is equal to 8. Our first step is to take Laplace transforms of both sides. So don't forget we've got a first and a second order differential equation here, so be careful of that. So we got 2 times the Laplace of the second order part of the equation, plus Laplace times the first order part of the differential equation. That's equal to the Laplace of 8. Again, using our equation 3 and 4, which we derived at the very beginning, or shown at the very beginning of the presentation, we will now get 2 times s squared times the Laplace of y minus s times the value of the function of y when x is equal to 0, take away the value of the first differential of y when x equals 0. That's our second order part, plus our first order part is the s times the Laplace of y, take away the value of y when x equals to 0. Don't forget on the right hand side the Laplace transform of 8. If you go to your Laplace transform tables, that will be 8 upon s. Step 2 here, we're going to impose the initial stated conditions. So when x is equal to 0, in this case y is equal to 0, and when the first differential equation when x is equal to 0, again the answer is 0. So we're just going to put those values into the equation. Basically they're going in here, here and here. Okay, as really very similar to the previous example, and that still equals to the 8 upon s. All I'm doing here is just simplifying the terms. Because I'm multiplying by 0 here and here, those terms will disappear, so I end up with 2 times the s squared times the Laplace of y plus s times the Laplace of y is equal to 8 upon s. Right, so simplify the equation here because our initial boundary conditions are all 0. Okay, step 3 here, we're going to rearrange the equation. The first thing I've done is factorised on the Laplace of y. If you check the previous line, this is the factorisation for the Laplace of y here, Laplace of y being the common factor, equals to 8 upon s. So I just divide both sides by the bracket, which is the 2s squared plus s in the bracket, and that leaves me with the Laplace of y on the left hand side. And all I've done on the next line is just factorise the bracket on s. I've just taken s outside the bracket, so I get s squared outside, and that leaves me 2s plus 1 inside the bracket. So a little bit of factorisation on the denominator there. Okay, step 4 here. We're going to work towards finding our inverse Laplace transforms. If we take the fraction on the previous page, we have 8 upon s squared and in brackets 2s plus 1. Now that s squared term is actually a repeated linear factor, so we need to be careful how we handle that. If you look at your previous work, we write that as a upon s plus b upon s squared. So those first two terms on the right hand side account for the s squared partial fraction, and then the 2s plus 1 we write as plus c over 2s plus 1. That's a linear factor, the 2s plus 1. On the next line, I'm making a common denominators both sides of the equation. So to do this, I have to factor the numerators, and again, just needs a bit of thinking through here. My original fraction on the right-hand side, first fraction is a upon s. So when I put the a over the s squared open bracket 2s plus 1, I've got to put s times the 2s plus 1 against it. Okay, because I must only have a upon s in this situation. If you see what cancels there, the brackets cancel, the 2s plus 1 cancels top and bottom, and the s cancels with the s squared on the bottom and leave me a upon s, which I must have. I cannot change the function. Same with the second term, the b should be b upon s squared, so if I'm going to write it over the 2s plus 1, I have to multiply the b by the 2s plus 1. Again, when it cancels, I end up back with b upon s squared. And finally, the c is actually over 2s plus 1, so I need to multiply that by an s squared if I'm going to put it over s squared, because again they cancel, and it leaves me with c upon 2s plus 1. I suggest you just take a moment to think that through for yourselves. All I'm doing now, once the denominator is the same, I can simply equate the numerators. So 8 on the left hand side, on the right hand side is as times open bracket 2s plus 1 plus b times open bracket 2s plus 1 plus c times s squared. All I'm doing on this last line on this slide is to just simply expand the first two brackets just for convenience. It makes it easier in a moment when we're doing our comparing coefficients. It just makes it easier to see the terms. So just expanding out 2 times a times the s squared there is as times 2s, and then 1 times as is giving me plus as. Then the b I get expanding the b times the 2s gives me 2bs, and then the b times the 1 gives me b. I've left the c times s squared as it is because there's nothing I need to do with that. So equation 2 here is a useful equation when I need to compare coefficients. Okay, I've just repeated equation 1 from the previous slide for convenience here, showing us our 3 partial fractions. Now I'm going to solve for the constants a, b and c now, but I'm going to start by solving for constants b and c using the cover-up rule. Don't forget the cover-up rule can be used to solve for all linear factors and the highest power of a repeated linear factor. So in this case our linear factor is the c upon the 2s plus 1, and our highest power of the repeated linear factor in this case is the b upon the s squared. if I take the solvent for the b first of all, don't forget with the cover-up rule we have to say what number do we need to make s to make the denominator go to 0. So when we're looking at the b value denominator, the s would be 0 in this case, and all we do then is cover up the s squared term on the left hand side of the equation, and we put the value of s wherever we see an s in the equation. So in this case the value of b is equal to the 8 in the numerator divided by 2 times s, 2 times 0, plus the 1. That gives us a value of 8 for b. Looking at my c constant, and denominator is 2s plus 1. What do I need to make s in this case to make that go to 0? I need to make s equals to minus 0.5. We put minus 0.5 into the left hand side, but of course this time we cover up the 2s plus 1 function, so we'll have basically c is equal to the 8 divided by the s squared, the minus 0.25 squared, and that will give us 32 for c. So b and c we found. I'm going to use the comparing coefficients method to find the final constant a, which I cannot find from the cover-up rule. So in this case, don't forget with comparing coefficients we generate equations on the s squared or the s or the constant term. We can actually generate 3 equations, and because we've already found b and c, I only need 1 equation to generate from comparing coefficients. So I'm going to compare coefficients of the s terms here. So what we do now is look at the left hand side of the equation 3. If I go back to my previous slide here, on the left hand side of equation c, you'll see there are no s terms here, but on the right hand side I've got an as term and I've got a 2bs term. So when I generate my equation here, I will have 0 on the left hand side but an a plus a 2b on the right hand side. I already know the value of b, and b is equal to 8 from the cover-up rule, so I get a plus 16 on the right hand side, and just transposing that for a is equal to minus 16 in this case. Okay, just writing my Laplace of y equals to the 3 partial fractions we're using here, and that's the a upon s, which is minus 16 upon s, plus my b, which is 8 upon s squared, plus my c was 32 upon 2s plus 1. If we look in our inverse Laplace transform tables, we can see in denominator we have an s on the bottom here, we have an s minus a on the bottom of this inverse Laplace transform, and an s squared on the bottom of this one. So we look now like we are orientating our partial fractions to the standard forms. All I've done now with this line here is I've just rearranged the term slightly, so I brought the positive term, the a upon s squared, in front of the negative term 16 upon s. That's just a convention really. But notice what I've done with this term, because I need to get the denominator in the form of s minus a, s plus a I've got here, but s minus a in the tables. I need to get rid of the 2 associated with the s. So what we do here is divide the top and bottom by 2. So dividing 32 by 2, we will get 16. Dividing the 2s by 2, we get 2s, and dividing the 1 by 2, we get 0.5. So now I've got my s plus a format on the bottom. Okay, so now I can write my functions in the correct format here. Looking at the first term, the 8 upon the s squared, that's in the format here of the 1 upon s squared. The h is the factor, so that will be 8 times x. If I look at the second partial fraction, the minus 16 upon s, that's in the this format here of the 1 upon s. That would go to 1, or in this case it will go to minus 16. Okay, and then the last format I've got is for the last fraction, the 16 upon s plus 0.5. Now notice the 0.5 is positive, but the standard form says a negative a, so our a in this case will be negative 0.5. So in that standard form I will get e to the ax, e to the minus 0.5x, and then of course I have to factor by the 16. All I've done on the next line is factorised on the 16. I will leave you with some tutorial exercises. These relate to linear and repeated linear factors only. No quadratic factors have been considered in this presentation. And also you may find that completing the square might be used in one or two of the questions, but I'll leave you to have an attempt at those. Don't forget the answers to the questions are given in the square brackets associated with each question here. Okay. Thank you for viewing.